Well, hello there, good people of the internet, and welcome back to another episode of Quantitative Bytes. So today we're going to be looking at part 2 of our two-part series on von Koch curves. So in the previous episode we looked at how to create the generator class that we're going to use. We'll recap the details in a moment, but I'll put a link to the previous episode up here. If you want to go and see that, you can. And in that episode we used the turtle graphics class that we've created previously to create a generator class that we could use to generate von Koch snowflakes or von Koch curves. And in fact, actually we made the effort to try and make it as generic as possible so that we could use it to create a much wider variety of different curves. And we're going to see today what kind of results we can actually achieve with that, which hopefully will be interesting. So as before, if you like this video, please remember to smash that like button, and please remember to subscribe to my channel if you haven't done so already, so that you don't have to miss any future videos. Anyway, listen, one thing I wanted to say, thank you so much to those of you who have subscribed to my channel. I have 19 subscribers now at the time of making this video, which is great. I'm really pleased about that, and really thank you very much indeed. And it really means a lot to me that there are people out there that are interested in the content I'm creating, and I just want you to know that I really appreciate you guys, and it's really motivating and helps me stay motivated to keep trying to make great content that is interesting. So thank you. Right, well, without much further ado, I think we should just jump straight in, and what we're going to do today is look at creating an initiator class. In the previous episode we talked about generators and initiators. I'm going to recap that in a moment, but we're going to create an initiator class, and then we're going to look at what we need to add to the CApp class that we've been using throughout this series since we started using the SDL library. So put a link up to the very first episode here if you want to go and check that out. And what we're going to do is create the von Koch initiator class, and then we're going to make the modifications to the CApp class that will enable us then to implement a recursive algorithm to actually generate von Koch curves, and particularly the classic von Koch snowflake. And then we're going to have a look at some other more crazy stuff that we can do with this algorithm. You'll see, if you watch to the end, you'll see that you can really make some really quite cool visual effects with this, but we'll come to that at the end anyway. We're going to focus on the classic von Koch snowflake first, and then look at the slightly crazier stuff afterwards. Okay, so I think we should just jump straight to it. Okay, so here we are. This is the classic von Koch snowflake, which we've probably all seen before, and which we covered in the previous episode. So I just want to spend just a little bit of time just to recap on what we did in the previous episode. So firstly, we talked about how we create a von Koch snowflake from two basic components, and these are the initiator and the generator. So the initiator is the shape that we begin with, and then the generator, which for a von Koch snowflake takes this form, is the object that we recursively replace each side of our initiator with. And that's what we're going to look at today, is how we implement that recursive algorithm. In the previous episode we talked about the geometry of the generator, and in particular we talked about how to implement this in a very generic way. So in principle, actually, this classic von Koch snowflake generator would be very easy to implement. It just has angles of 60 degrees and so on, and that's really not that difficult to do. But what we set out to do was to create a generator class that could be used to create a wide variety of different generator geometries. And this, of course, made the problem slightly more complicated than perhaps it needs to be. But as we'll see towards the end of this video, the fact that we made it as generic as we did will allow us to create some really quite cool results. But we're going to come to that, as I say. So watch to the end if you don't want to miss that. So we stated that the particular problem with the geometry is given a starting point and an ending point, and then a number of user-specified nodes, n, each with an angle of theta n, each of a user-specified angle. We had to compute the length of each edge, and this, of course, is the step length for our turtle. Okay, so we're using the turtle graphics class that we created before in a previous episode. I'll put a link to all the previous episodes in the description below. And we did a basic analysis of the geometry of the situation, and then we realized in this particular scenario that we have these particular angles going on, 60 degrees here at the first node, and then minus 120 degrees at the second node. And then we looked at how we can actually calculate the edge length as simply being the total length divided by the number of segments, and we could calculate the number of segments simply using basic trigonometry. But what I want to talk about today is how we actually go about implementing a recursive algorithm based on this generator to actually create the snowflake, or indeed the von Koch curve. Now it's worth noting actually the von Koch curve is simply defined between one start point and one end point. To create the classic snowflake, we use the equilateral triangle as our initiator, which is actually slightly different to the original von Koch curve. Anyway, to begin with, what we're doing is we have a start point defined and we have an end point defined, okay? And then we simply draw an instance, or create an instance of our generator between that start point and that end point, okay? So that's the first level of the recursion, level 1 of the recursion. And then what we do is we now define a start point is in the same place and the end point now becomes here. So what we've done is we're defining our start point and end point to correspond to the first edge of the initial generator. And what we're going to do is replace this edge with another instance of the generator, which becomes like that. And this is why it's so important that we took the time to look at the geometry and how to calculate these edge lengths, because obviously this instance of the generator, whilst it has exactly the same shape as the previous one, it has to be smaller and everything has to scale proportionally, okay? So once we've done that, we then move on to the next edge of the first generator that we use. So we look, start point is now here and our end point is here, and we're going to replace this edge with another instance of the generator, like so. And then we move on to this edge, so now the start point is here, the end point is here, and now we're going to replace this third edge of the initial generator with another instance of the generator, like so. And then finally, we define our start point here and our end point here, and this is the final edge, the fourth edge of our generator, and we're going to replace that with an instance of the whole generator, like so. So this would now correspond to level 2 of our recursion, of our recursive algorithm, okay? So each edge of the initial generator has now been replaced with a scaled down but complete copy of the generator. And then for generation 3, I think you can probably see what we're going to do. We're simply going to repeat that same process again, exactly the same. So now we set the start point here and the end point here. So now we're taking the first edge of all of these edges that we now have, and we're going to replace that edge with a yet smaller but also complete copy of the generator. And we will do that so on and so forth across all of these edges, and that would then correspond to generation 3. And then if we wanted to go to generation 4, which we can't really show obviously with these quite thick lines, but for generation 4 we would then replace each one of these small edges with a complete copy of, but scaled down copy of the generator. And so you can see this is how we form the classic von Koch curve. So this is actually the von Koch curve defined between one start point and one end point. So what we do to create the snowflake is we start with an equilateral triangle, and we simply draw instances of the generator between the corners of the triangle, between the points that define the triangle, and then we simply go through the same iterative process. Okay, so that's what we're going to do, and I really hope that everything will become clear about how this works when we actually look at the code to do this. We're not really going to look at any complex geometry or anything like that today. We covered all of that in the previous episode. So what I want to do now really is jump straight into how we actually write the code to make this happen. So I'm going to go to my text editor, which is here. Now, we're going to create a new class in our system. So I'm starting out with the code from the previous episode. Okay, so if we just look in the terminal window, here we are. So this is the code we have from the previous episode. We have the CApp class, we have our main function, we have our QBTurtle class, and we have the QBVKGenerator class. So all of this is what we have from the previous episode. Okay, so if you've been following along, you should have this code already. If not, then I suggest you go back to the previous episode and look back through the previous episodes, and then you can work your way up to get this code base here. What we're creating today in terms of a new class is these two files here. So I've created two new files, which are QBVKinitiator.h and QBVKinitiator.cpp. Okay, and these are going to contain our initiator class. Now, strictly speaking, it probably isn't necessary to actually create a class to deal with the initiator, but it does bring about some advantages in terms of how we can actually go on to use it. And like I say, in keeping with our whole approach, we've been trying to keep everything as generic as possible. I think this is a good way to go. So I'm in my text editor. You can use any text editor that you like, or an integrated development environment if you're following along that way. That will work as well. And we are going to start fleshing out the code for our qbvkinitiator.h, so the header file for our new class. So we start out with, of course, our include guards. So if n #fndef qbvkinitiator.h. So if that's not defined, then we define it. We've talked about include guards many times. Initiator h and #endif. Okay, go ahead and save that. Right, there we go. So this is qbvkinitiator.h. Now, we need to include just one thing into this. We're going to need the vector class from the standard libraries. And we're going to define our class as qbvkinitiator, like so. Okay, and let's just make that nice and tidy. So in terms of public functions, we obviously have our constructor, destructor pair. Now, probably, I don't think we're not really going to do anything with those, but I always think it's good practice to just bother to define them. So qbvkinitiator is the constructor, and qbvkinitiator is our destructor. And then we're going to define functions to allow the user to interact with the generator. Interact with the generator. So the whole point of this is that the user can specify a generator of any particular shape that they like. Okay. First of all, we need a function that will allow the user to add vertex to the system. They can have any number of vertices, so obviously an equilateral triangle would have 3. So we're going to define our function addVertex, which will return void or no return, and will accept xpos and ypos as floating point inputs, so specify the x and y coordinates of each vertex. We're going to have a function numEdges that will return the number of edges. Okay, that should be numEdges, I think. There we go. And finally, we're going to define a getEdge function, which returns a boolean to say whether or not retrieving the edge was successful. And this is going to accept a pointer to x1, so float star x1, float star y1, and float star x2, and float star y2. So those are pointers to x1, y1, x2, and y2. So we can use those to return our values. And it accepts as input also an index. Now finally, we need to define a couple of private things. We need to store our vertices. So we do it as std vector of type float m underscore vertex x for the x locations of all our vertices, and std vector float m vertex y for the y locations. So if we go ahead and save that, that is everything that we need for qbvkinitiator.h. It's really a very simple class, and like I say, maybe sort of will make you think, well, do we really need to define a class to do that? And like I say, probably technically no, but I think just in keeping everything as generic as possible, this is quite a nice way of doing it. So now I'm going to look in qbvkinitiator.cpp. Okay. Very first thing we're going to do is to #include qbvkinitiator.h, h that we've just defined. So save that. Okay. Now we have constructor and destructors. We don't put any code in those. So just to save a bit of time, I'm just going to copy and paste those in. You don't need to see me typing those. So the first function we need to define is the function to allow the user to add a vertex. So we have qbvkinitiator : add vertex, which accepts as input xpos, float xpos, and float ypos, like so. And this is very simple. All we need to do is m vertex x dot pushback xpos and m vertex y. Is that right? Yep. Dot pushback ypos. There we go. Very, very simple. Okay. And then we need our function that is going to return the number of edges. So returns an int. This is qbvkinitiator colon colon num edges, like so. And yes, we're going to insist, because we are defining, automatically defining closed shapes. So that's where creating this as a class really comes in. It means we can do that. We're going to set the condition that there must be at least 3 vertices defined, okay, before we do anything. Okay, so if m vertex x dot size is less than 3, then simply return -1 to indicate an error condition. Else, we're simply going to return return m vertex x dot size, just like that. So very, very simple. Now I'm just going to put some blank lines in there so I can keep typing towards the middle of the screen, which I think is easier for you guys to see what's going on. And now finally, we're going to define our function that will allow us to retrieve each edge of the initiator. So this is qb_vk initiator colon colon get edge. And the return type of this is Boolean, because it's going to return true or false, depending on whether or not the operation was successful. And it accepts as input float star x1, float star y1, float star x2, and float star y2, and int index. So index is the index of the edge that we want to retrieve. x1, y1, x2, and y2 we're going to use to actually return the value. So the first thing we need to do is check that index is valid. Okay, so if index is greater than or equal to m vertex x dot size, like so, then we simply return false, okay, because we don't need to do anything. Now, if that isn't the case, then we're simply going to set the value of x1, so we do star x1 is equal to m vertex x index, okay, and the star y1 is m vertex index, like so. And now we need to do things a little bit differently. Because we're going to automatically close the shape at the end, we need to consider if our index is corresponding to the very last edge, which will be the one that automatically goes from the last vertex back to the first one, then we need to do something a little bit differently. So let's just have a look how that works. So what we do, if we have if index is less than m vertex x dot size -1, okay, in that case, what we're going to do, star x2 is going to be equal to m vertex x, square brackets index plus 1, okay, and star y2 is going to be m vertex y index plus 1, okay. So what's going to happen in that case, x1 and y1 are going to be set to whatever index is. If index is, say, 0, so those will give them the first coordinates of the first vertex, and then x2 and y2 will be set to the values pointed to index plus 1, which will then be the second vertex. If index is 1, then these are going to be the second vertex at index 1, and these will then be the third, and so on. If you work through that, I think you should be able to see how it works. So if index is not less than the number of vertices -1, then we know that the last point has to be equal to the first vertex. So we set this to vertex m vertex x 0, okay, and star y2 is m vertex y 0, like so. Okay, and save that. And that is actually everything that we need. So what this will do is set x1 and y1 to the first vertex of any particular edge, and then it will set x2 and y2 to being the second vertex of that edge, or if our edge index corresponds to the last edge of the shape, it automatically sets x2 and y2 to be equal to the first vertex that was specified. So that will automatically close the shape. So for an equilateral triangle, we specify 3 vertices, and so edge 1 going to be the edge between vertex 0 and vertex 1, edge 2 will be the edge between vertex 1 and vertex 2, but then edge 3 will automatically be completed as being the edge between vertex 3 and vertex 1. Okay, so let's save that. That is everything that we need for our QB, for our initiator class. Okay, so quite simple. Now, we're going to need to make some changes now to actually make this code do something. So we're going to go into capp.h. So capp.h and capp.cpp. These are the definitions of the CApp class that we've been creating iteratively as we've been following along. So we need to make some changes. Obviously we need to use the initiator. So first of all, we're going to hash include qbvk initiator.h, like so, right? So that's quite simple. And then what we're going to do is we are going to simply create an instance of that we can use. So here we go, make an instance of our initiator class. Okay, so it's qbvk initiator mvk initiator, just like that. Now, one final thing, we're going to need to add a new function to our CApp class, and we're going to put the definition here. It's a private function. It will return void, and we're going to call it, oops, if I could spell, draw edge. Okay. Now, this is going to accept as input float x1. Note, these are not pointers. Okay, float y1, float x2, and float y2, and int level. And let's save that. So that is everything we need to add to CApp.h. Okay, so actually the next thing that we need to look at is the App.cpp code. But one thing that does just occur to me, if we go back to qbvk initiator.cpp and we look at our getEdge method, this is supposed to return a boolean, and we have already detected that if index is greater than or equal to the vertex size, the number of vertices, so if we have an invalid index specified, we return false. But we should, of course, after finishing everything successfully, return true. There we go, let's just space that out. There we go. So I forgot about that originally, but there we go. Okay, so App.cpp, we've just been modifying App.h. We put the qbvk initiator class in there and everything else. So in App.cpp, let's have a look at what we need to do here. At the top of App.cpp, we need to hash include vector to bring that in from the standard libraries. We're going to need the vector class. Now we don't need to do anything really at the top there. What we need to do is find the onInit function. So that's the constructor. We're looking for the onInit functions. As with the previous episode, we're going to put all our code in there so that it'll run immediately when we come to run the code. And this is the code here that we have from the previous episode. Okay, so everything between SDL render clear and SDL render present. This is the code from the previous episode. We don't need that, so we can simply delete that now. Okay. And in here we are now going to put in our code for this specific episode. So the first thing that we're going to do is to set up our initiator. Okay, so this is mvk initiator, and we're going to add 3 vertices to this to create an equilateral triangle. So we're going to do add vertex at 120, 340, mvk initiator add vertex 320, 40, and mvk initiator add vertex at 520, 340, like that. Okay, and then we're also going to need, apologies, that is not how you do a comment in C++. Okay, so we're also going to need to set up the generator. This is mvk generator, add node. So we're going to add our 2 nodes. We're going to initially just do what we need to do for the classic von Koch curve, von Koch snowflake. So there'll be 60 degrees and minus 120 degrees. We did discuss that in the previous episode. And then we're actually going to need our code that's really going to make this work. So we are going to loop through each edge of the initiator and apply the generator as we go. Okay, so first of all, we're going to do SDL set render draw color, P renderer, pointer to our renderer. We're going to go for white, which is 255, 255, 255, and an alpha of 255. We don't want any transparency. We need to declare variables x1, y1, x2, and y2, which we can use to retrieve the coordinates of the edge. And then we're going to loop through our edges. So I equals 0, for int I equals 0, I is less than mvk initiator dot num edges, like so, plus I, just like that. And then because the getEdge method from vk_initiator returns a boolean, we can put it inside a conditional statement. So we do if mk vk_initiator.getEdge, and we pass a reference to x1, reference to y1, reference to x2, reference to y2, and pass I as our index, like so. If that is successful, then we are going to call the drawEdge function. Now we literally in capp.h, we have just defined the prototype for that, but we're going to come to actually the function definition in a minute. So we do x1, y1, x2, y2, and our initial level. So initially we're going to do a level of 1, okay? So that is actually it, everything that we need really to do the basic drawing. So all of the clever stuff, all of the interesting stuff that we're going to do really is going to come in the drawEdge function. We're going to put that in here, so we're going to put that between the onInit function and the onExecute function. It doesn't really matter where it goes. It doesn't have a return type, so we avoid capp::drawEdge, and it accepts as input float x1, float y1, float x2, float y2, and int level. Okay, so this is actually going to implement our recursive algorithm. So this function is going to be calling itself, and each time it does that, it's going to decrement level. So level is our variable that specifies how many levels of recursion that we want. So if we call drawEdge with a level of 1, we only want it to run through once. If we call with level 2, then obviously 2, and so on. So the very first thing that we need to do here is to decrement the level. So as soon as we come into this function, we decrement the level by 1. Now you'll see why that's important in a moment. We're then going to need to set up arrays to store our data. Now I'm just going to save a little bit of time, copy and paste that from over here. Okay, so we define our 4 arrays, edge x1, edge y1, edge x2, and edge y2, of using the vector class in the standard libraries, and we're going to use those to store the points and all of the edges for the generator for this particular level. That I hope will become obvious in a moment. And then we need these floating point variables to handle the returned endpoints from each edge. Okay, so now what we're going to do is we're going to set up the generator and call the compute function. So bear in mind we've already configured our generator. We only have one instance of the generator class, and we've already set it up here with our node, so we don't need to worry about that. So the shape of the generator is already defined. So what we need to do just here is mvk generator. There we go. We just need to set the start point to x1, y1, and mvk generator set endpoint x2, y2, like so, mvk generator dot compute, and we call the compute method. So if we look at the diagram, what we've done is we're specifying the start point there and the end point. We're going to for our first level, and then we call compute that will calculate the edge lengths and calculate the coordinates of all of these other points. So all we need to do then is to retrieve those points from the system and store them. Okay, so this is really very simple code. So all we're going to do, in fact, let's just save a little bit of time. You don't need to watch me typing everything out all the time. So we're simply going to loop through that. So all we do is we loop through each edge of the generator, so just using a loop with j, and we call the getEdge function from the generator class, and we pass the references to gx1, gy1, gx2, and gy2, these variables we defined here, and the index of j, or the edge number that we want, is j, and then if that is successful, then we simply store those coordinates into these 4 arrays that we defined up here. So that's quite simple. But now we get to the really interesting bit. Okay, so now we are going to loop through each edge of the generator again, but this time we either draw the edge if level is equal to 0, or we recursively call this function to repeat the process for the next level. Okay, so let's have a look at what that actually means in code. Okay, right, so we have for int j equals 0, j less than mvk generator.numEdges plus j. Okay, there's our loop. Now, if level is equal to 0, in this condition, so in this case, we actually want to draw stuff. Okay, so remember we decremented level at the start of the function, so if level starts out at 1, indicating we want one loop through the recursion, then this is immediately decremented, which will mean it'll be 0, which means that in that instance we will be drawing stuff immediately. So here we have SDL render draw line to p renderer, comma, static cast to int of round edge x1j, like so, to static cast to int of round edge y1 of j, like so, comma, static cast to int round edge x2j, and to static cast to int round edge y2 of j, 1, 2, and 3 parentheses. Okay, so in the condition that level is equal to 0, we will render our stuff. If that isn't the case, and this is the clever bit, if that isn't the case, we now recursively call the draw edge function again, and this time we specify the starting point as edge x1j, edge y1j, and the end point is edge x2j and edge y2j, and we pass level like so. And that is actually everything that we need. Okay, and I think if you work through that, particularly with reference to the diagram, so what we've done, so the first time we come through that recursive loop, if levels was more than 1, our original start point and end point would be here, and so we set this up with the start point and end point to the generator class, and then we call the compute function that calculates the coordinates of all of these intermediate points. And then we store those points in an array. And then if level is still not equal to 0, we take each one of those points from the array, from those arrays, and we use that then as the start point and end point, and then we repeat the whole process. So you can see when we then call the draw edge function again, it's then going to now set start point and end point for the generator to here and here, and that's obviously going to compute the generator between those points like that, and then that's going to repeat through the process. I think if you look at that diagram and look at it in connection with the code, I think you should see how that works. It's a really nice demonstration, I think, of a recursive algorithm. It isn't really too complicated, but it is just, I feel, a really nice example of what you can do with a recursive algorithm. So, okay, now we should go ahead and have a look at compiling our code, and let's have a look at what we get. So we need, let's start our compiler, g++ -o main, that's the executable that we want to make. I don't think we need to change anything else beyond capp. So anyway, we need to compile main.cpp, capp.cpp, qbvk, generator.cpp, qbvk, initiator.cpp, and qbturtle.cpp. And then we need -l SDL2 to tell the linker that we need to link against the SDL libraries. Okay, and that ran without any problems. So let's run our code and see what we get. Here we are, and there we go. So that is the level 1 von Koch Snowflake. So we can see where the shape of the originator was. You can see the 3 sides, and we can see that each side of that equilateral triangle has been replaced by a complete copy of the generator that we defined. So let's close that. Now, okay, we don't need that. Let's go back to, here we are. Now, let's set our number of levels, initial levels, to 2, and let's compile that and run it again and see what we get. And there we go. So now we see this is the level 2 of von Koch Snowflake, and we can see we're getting increased levels of detail. And you can see if we were to take this side of the original triangle that originally had this generator defined, and you can see that each edge of that generator has now been replaced by a scaled down but complete copy of the generator. And if we put initial levels up to 3, then we can see how that works. And there we go. So in that case, this is the level 3 von Koch Snowflake, and we see that we're starting to get the increased levels of detail and everything going on. Okay, and yes, I think that's kind of cool. Okay, so that's really it for the basic von Koch Snowflake. That is everything that we need to do to really make that work. We've implemented the recursive algorithm and we've talked about how that works, and you can set the number of levels and we can create the basic or classic von Koch snowflake, which is kind of cool. Now, I mentioned at the beginning that all the effort we went to make the generator class as generic as possible and using a particular initiator class meant that we could go on to create some really interesting shapes. So I'm going to have a look at those. So these new shapes, these are not von Koch curves or von Koch snowflakes, I don't think. I think that just covers the basic shape here. But I just want to show how you can play around with the parameters for the generator and the initiator to create some really quite cool results. So let's just have a quick look at that now. So the first thing that we can do is we went to quite a lot of effort to make our generator class as generic as possible. So let's just have a look at what happens if we change that. So if we add some nodes, we're going to add an extra node at 0 degrees, which will equate to simply no rotation. Okay, so it means carry on in the direction that we're already going, and add node 120F. So we looked at this shape for the generator in the previous episode, and it's just kind of fun to have a look at what that gives us. We're going to leave levels at 3. Okay, let's go to our terminal window, run our compiler, and run our code. And there we go. So now we see we get something really quite different indeed, which is starting to look really quite interesting. And actually, I think this shape still has this isn't technically a von Koch snowflake anymore, of course. I think the von Koch curve really only covers the classic shape. So we've deviated away from that now. But I believe this shape still has some of the same geometrical properties. It's obviously still a fractal. If you were to zoom into it, it will exhibit self-similarity. At all levels, obviously, if you created enough levels. And also, I believe it's non-self-intersecting, which I think is one of the criteria. I haven't really sort of explored that in any detail. I'm not offering a mathematical proof of that or anything like that, but I think it's pretty interesting anyway. Let's have a look at another example. So one of the other types of generators that we looked at had square edges, so we created essentially like a square wave. So we're going to do that now. So let's comment out the nodes that we added previously. And we are going to do 90 generator add node minus 90, like so, and MVK generator add node and minus 90. So that will give us the square wave. I think we explored that in the previous episode. Let's have a look at how that looks. Yes, and there we go. So you start to see how it's possible to create some really fascinating shapes and patterns, and this is quite an interesting one. Let's just have a look at what happens if we decrease the number of levels, but let's put number of levels down to 1 and run that. So we can see what's happening. So that's with number of levels equal to 1, and we see each edge of our initiator has now been replaced by this square wave. Okay, and then if we go, if we set levels to 2, let's run our compiler again. So now we see that each of those was replaced by the square wave, and then we've taken each edge of that square wave and replaced it by the same shape again. But obviously this no longer exhibits the same kind of non-self-intersecting shape. It's really quite a fascinating shape. And just to really show the flexibility, I think, of this, one thing that I think is kind of cool, let's just put all of these nodes in together. Let's just put, oops, there we go, let's put everything in that we've just created and have a look at what we get with that. Okay, and that really starts to give something that kind of looks a little bit crazy. I mean, I think that's kind of cool. It should exhibit the same kind of fractal self-similarity of these generic curves, but clearly we've broken the rules now about non-self-intersecting, I should think. But it just goes to show how you can really just play around with this and really create some interesting results, play around with adding nodes, different numbers of nodes, different angles, all that kind of thing. And you can really make some really quite fascinating results. It's I think, quite good fun to play around with. I had quite a lot of fun coming up with this and creating these. And this was the point, really why in the previous episode we went to so much work to create the generator class to be as generic as possible, because that really then allows us to do this kind of thing, and to do it quite easily. We can explore all sorts of different possible shapes. The other thing that you can also do, of course, is to vary the shape of the initiator. I'm not going to do that now. That's an exercise I can leave for you. Feel free to add more nodes or whatever to the initiator, create different shapes, play around with the generator class, add, remove nodes at different angles and things, and just play around with it, see what kind of results that you can get. It's really quite, I think it's really quite fascinating. That is everything that I really wanted to talk about today, and that completes or concludes our two-part series on von Koch snowflakes or von Koch curves. And we've looked at how we can generate the classic von Koch snowflake with our recursive algorithm, and then we've shown how the effort that we went to, particularly in the previous episode, to create the generator class to be as generic as possible, allows us to really play around with this and really have some fun and create some really quite interesting and quite fascinating shapes and patterns, which, well, I think is a lot of fun, and I hope at least some of you will too. But look, as I say, that's really everything I wanted to talk about today. And if you've liked this video, please hit that like button, and please remember to subscribe to my channel so you don't have to miss any future videos. Listen, I really hope you've enjoyed it, and I hope you got something useful out of it. It's been a pleasure for me making this video, and as I said at the beginning, thank you so much to all those of you that have subscribed to my channel so far. That really means a lot to me, and it's really motivating for me to know that there are people out there that care about the content that I create and are obviously interested in watching it. So thank you very much. And yes, so that just leaves me to say that I really look forward to seeing you in the next episode. Thank you very much for watching. It's been a pleasure. Bye.